1961, Lecture 4, The Conservation of Energy. October 6, 1961, Lecture 4, The Conservation of Energy. October 6, 1961, Lecture 4, The Conservation of Energy. October 6, 1961, Lecture 4, The Conservation of Energy. 1961, Lecture 4. October 6, 1961, Lecture 4.
No summary of the previous lecture. There's no summary of the previous lecture, just to remember whatever you can remember from it. No vital points. The next two lectures after today will be given by Professor Matt Sands, because I'm going to a meeting in Brussels. So, and I'll come back next Tuesday, the Tuesday following. Today's lecture is on one of the laws of physics, and beginning, of course, the detail looking at the different aspects of physics. We've just finished our description of things in general, and now we look at more specifically, in particular, what a law of physics looks like. And so I picked one out to illustrate the ideas and the kind of reasoning that might be used in, say, theoretical physics. So the lecture today is on the conservation of energy. There is a fact, or if you want to call it a law, governing all natural phenomena that's known to date. There's no exception known to this. It's exact as far as we know. And the law is called the conservation of energy. It states, there is a certain quantity, which we call energy, that doesn't change in the manifold changes which nature undergoes. Now that's a very abstract idea, because it's a mathematical principle. It says that there's a numerical quantity that doesn't change when something happens. It's not a description of a mechanism or anything. It's just a strange fact that you can calculate some number, and when you're all finished watching nature go through her tricks, you calculate the number again, and it's the same. Something like, the bishop is on the red square now, and after a number of moves, details unknown, it's still on some red square. It's a law of this nature. Since it's an abstract idea, I would like to illustrate the meaning of it with a rather silly example, but it does illustrate the idea. I want you to imagine a child, perhaps Dennis the Menace, who has blocks. But you must appreciate that these blocks are absolutely indestructible and cannot be divided in pieces. They're just, each is the same as the others. And we'll suppose that he has, say, 28 blocks. Now this child is put into a room by his mother in the beginning of the day with his 28 blocks. And at the end of the day, I don't know why she's so curious, but she counts the blocks very carefully and discovers a phenomenal law that no matter what he does with the blocks, there are always 28 blocks. So this goes on for a number of days until one day there are 27 blocks. But a little looking around shows that there's some under the rug. You have to be careful to make sure that you look everywhere in order to make sure that the number of blocks doesn't change. One day, however, the number of blocks appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and now looking outside, you can find the other 2 blocks. So you bring them back in again, and everything's all right. Another day, careful count indicates the existence of 30 blocks. This causes a considerable consternation until it's realized that Bruce came to visit, and he owns blocks. And left perhaps a few. So after we've gotten rid of some of these things, that we close the window, we don't let Bruce in, then we see everything's going along all right until one time when we count there are 25 blocks. But there's a box in the room, the toy box that the boy has, and the mother goes to open the toy box, but the boy says, "No, don't open my toy box," and screams. He doesn't want them. The mother is not allowed to open the toy box. Being, however, extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces, say. So the next time when she wants to check, she weighs the box again, subtract 16 ounces, and divide by 3. So she discovers the following number of blocks that you can see that you have to add to this number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces, and then it's constant every time, up to a point. There then becomes some gradual deviations. There appear some deviations, but careful study indicates that that dirty water that's in the bathtub is changing its level. In other words, the child is throwing blocks into the water. You can't see it because it's so dirty, but you can find out how many blocks are in the water by adding another term to this formula, which is height of water in tub minus 6 inches divided by 1/4 of an inch, because each block that goes in is 1/4 of an inch. And so with a gradual increase in the complexity of the world, you find a whole series of terms representing ways of calculating how many blocks are in places where you're not allowed to look. And as a result of this, it's possible to find a complex formula, a quantity which has to be computed, which always stays the same in this situation. Now, I would now describe the analog of this to the conservation of energy. The most remarkable aspect of it is that I want you to abstract from this picture, first, there are no blocks. You never see the blocks, so you take away that term. Then you discover yourself calculating more or less abstract things. The analog has the following points in it. First, sometimes when you're figuring out the energy, some of it leaves the system and goes away, or sometimes some comes in. So in order to verify the conservation of energy, you've got to be careful that you haven't put any in or taken any out. Second, that energy has a large number of different forms, and that there's a formula for every one of the different forms. I've written a number of the forms here. I see I left out elastic energy. And there's a formula for every one of these things, and we find out what the formulas are, and then total them up. It won't change except for going in and out. I'll give you that. Well, we can leave that down if you want. So that's the relation of the analogy. It is important to realize that in physics today, we do not have any knowledge of what energy is. My analogy is bad because we do not have a picture in physics today that energy comes in little blobs of a definite amount. It does not that way. And it is not the definite blocks, but there are formulas for calculating some numerical quantity. When you add it all together, it gives 28. Always the same. We have no deeper understanding of it than this. And it is an abstract thing and doesn't tell you the mechanism or the reasons for the various formulas. Now, the conservation of energy can only be understood if we have the formula for all these things. And I could, of course, list the various formulas for different forms of energy. We call these things different forms of energy, different hidden ways of calculating the number of blocks. However, I want to amuse us today by discussing the formula for gravitational energy around on the surface of the Earth here, not going very far away. And I wanted to derive this formula